All right, so yesterday we were talking about work energy theorem. Okay, we talked about how work is a change in mechanical energy. Okay, how that could end up being force times distance is our final mechanical energy minus our initial mechanical energy. Okay, we did a bunch of problem solving related to that. Okay, we'll kind of come back to that here or there, but okay, we've kind of done the instructional part of that already. Now, question on the board here says, I hold this object, okay, above the ground like this, okay? How much work is done to do this? Okay, the answer's up there, it's 0, but why is it 0? Okay, it's not moving as part of it. Like, if it's not moving, what am I not changing? It's kinetic or potential energy, right? It doesn't require any work if I don't change its energy, okay? It's not going any higher, so it's not gaining or losing any potential energy. It's not going faster, so it's not gaining or losing any kinetic energy either. If something is just being held perfectly still, there's no work being done on it because its energy isn't changing. There's a lot of times where I'll put a question like that in the multiple choice of a unit exam, and people will go about doing calculations for it, okay? And they just don't realize that if the object, if there's no change in energy, then there's no work. To just hold something still doesn't change its energy in any way, okay? It's one of those checking your understanding kind of questions, okay? Does that sort of make sense? All right, so today we're going to look specifically at the two different kinds of energy, kinetic and potential. We're going to do some problem solving, and then tomorrow is going to be your quiz. Now your quiz is not on work and energy, okay? I put practice quizzes up there last week. It was 5, 6, and 7 for this week, okay? That's Newton's third law, friction, okay? That kind of stuff. So expect 2-box, 3-box questions, questions involving mu is times normal force equals force of friction, okay? Those kind of questions are what you're going to see on tomorrow's quiz. So if you haven't done those 3 practice quizzes, that is what is on those 3 practice quizzes and tomorrow's quiz. Okay, so make sure you do some practice tonight if you haven't already. Okay, let's talk about the different kinds of energy here. Okay, so gravitational potential energy. Okay, this is energy due to position. Okay, the further an object is from the ground, or the further that object can fall, the more potential energy it has. Okay, what other things could affect an object's potential energy besides height? Yeah, definitely mass. I mean, which would hurt you more? A tennis ball dropped from the top of the Calgary Tower or a piano? Okay, I mean, they're going to be going the same speed when they hit you. I'd much rather get hit by the tennis ball. It'd probably still hurt, but it wouldn't hurt me near as bad as the piano. Okay, the piano simply has more mass. Thus, it has more ability to do work. Okay, what else? What else could affect an object's potential energy?
Gravitational force?
Exactly. Or acceleration due to gravity, yeah, which relates to the force. If I'm looking at something falling on Earth from 3 meters, that could have a lot of potential energy. Something on the moon falling from 3 meters isn't nearly as dangerous because it's not going to get going nearly as fast, because on the moon, g is only 1.6 meters per second squared. Okay, it's a lot less than gravitational acceleration here. Okay, everybody all right with that idea? Okay. Now, where this formula kind of comes from, okay, are m times g times h. A change in potential energy is still caused by work. That's still force times distance. But what force does the work in gravitational potential energy? What force do you work against if you're going to give something gravitational potential energy? It's not a trick.
Gravity.
Gravity. How do we calculate the force of gravity? Mass times gravity. Okay, so there's the force. What distance, what do we call the distance when we're talking vertical? It's force of gravity times distance, right? M times G times H is force times vertical distance. Okay, that's where that formula comes from. Okay, everybody all right with that? Hopefully that's somewhat familiar from Science 10. Okay. Okay, I'd like you guys to write this one down and try it. Very simple, like this is a Science 10 question. Okay, nothing like what we did yesterday. Car and its passengers have a mass of 500 kilograms. What is their change in gravitational potential energy if they are lifted from the ground to a height of 48 meters? Okay, so without like really overthinking this, change in anything is final minus initial. Since this thing starts on the ground, what's its initial potential energy? Okay, M times G times H final. 500 kilograms times 9.81 times 48 meters. Oh, I forgot to start my calculator this morning. Okay, so we're looking at 2.35 times 10 to the 5 joules. Okay, it's a lot because it's a lot of mass. And well, it's 48 meters, so it's pretty high. Okay, all right, everybody okay with that one? Right, nothing too mathematically taxing there. Okay. Copy that one down. You probably want to do a rough version of the diagram as well. Okay. Or again, we're just looking at change in gravitational potential energy here. Okay. Give you a few minutes on that one, and we'll walk through it. All right. So the thing that this question is trying to point out is the importance of a reference point when you're calculating the gravitational potential energy. The most common reference point for gravitational potential energy is ground level. Okay? But sometimes a question will say, what's the change in gravitational potential energy from like the 3rd floor of a building to the 10th floor? In that case, the reference point is not ground level, it's the 3rd floor. So you always have to kind of watch that in a question here. Okay, so it says the track is set up. What's the gravitational potential energy of the car, which has a mass of 0.025 relative to the floor? So now ground level is our reference point there. Okay, so we would go delta EP is going to be EP final minus EP initial on the floor. That's 0. Okay, times 2.15 meters. That's how high it is from the floor. All right, so we should get 0.53 joules. Not very much, but it's also not a very heavy car. Okay, calculate the change in gravitational potential energy of the car when it arrives at the bottom of the hill. Okay, so that's going to mean, okay, another one of these calculations, except now it's going to be EP final minus 0.53 joules. That's our initial. Okay. Is it going to give me a negative number here? Is that okay? It is. It's lost that potential energy. As it goes down the hill in a perfect physical world, all that potential is turned into kinetic. Okay? So it's okay that we get a negative number here. We should. Okay, so all we have to do is go 0.0250 times 9.81 times 0.950, and then subtract 0.53 joules. Okay, so we do get a negative number. That's okay. We've lost potential energy. That is our change. It's negative. Okay, everybody all right with that one? Okay. So a question like that is not going to be something that would be a written response item worth a lot of marks on the test. It could be a numerical response question, okay, because it does require you to do some simple calculations. But here's the thing, with numerical response questions, okay, and we haven't had one like this yet, but okay, I can build them so that you've got your answer thing here, okay, and one of the options is a decimal place, right, and one of them is positive or negative. Okay, that's just a negative. If you don't fill it in, then the computer defaults positive. But okay, on a case like that, somebody might do it backwards, put it in without the negative, and get it wrong. Okay, this is one of those. I'm not checking your math, and I'm checking your understanding. Do you understand that it makes sense in this situation to get a negative number? Okay, that the work represents a loss in energy. Okay, I would like you guys to try those two. Well, let's just try one for right now because it's all I can fit on there. Okay, now just so you understand context, a pile driver is something used to pound pilings into the ground. Pilings are footings, things you put, like you build a deck or a building on. Okay, they go down below the frost line so that they don't heave. Okay, this is not the wrestling move, okay, where you turn a person upside down and bounce them on their head. Although it's aptly named pile driver because it looks a lot like what a pile driver does. It takes a mass and pounds it into the ground. Okay, so all you do with a pile driver is you take this big heavy mass and you lift it up above the ground and then you drop it. Okay, and it lands on the piling and pounds it into the ground like a big hammer. Okay, so you can picture it in your mind what's going on with the context of the question. That's what a pile driver does. Okay. Okay, guys, without overthinking these here, okay, calculate the maximum potential energy at its highest point. Okay, it's just M times G times H. So that's 550 kilograms times 9.81 times 12.5 meters. Okay, and so that's going to give us okay, 67,443. We only have 3 significant digits there, so 6.74 times 10 to the 4. Joules. Okay, and then also at its lowest point, that would be at 2.3 meters. So 550 times 9.81 times now 2.3. Okay, 12, so 1.24 times 10 to the 4 joules. All right, then it says, what is the change in potential energy if lifted from the top of the pile to its highest point? Okay, so final minus initial. Final is 6.74. The initial is on the top of the pile. All right, so we got 5.5 times 10 to the 4. And that's positive. It's being lifted, it's gaining that energy. Okay? Everybody all right with that? I'd like you to try number 3. We did something like this a little bit yesterday. Okay, you got a winch pulling a 250 kilogram block up a 20 meter long inclined plane. that is tilted 35 degrees to the horizontal. We only want the change in gravitational potential energy for this one. There are two ways to do this one. One short way, one much longer way. Okay? So they tell us that the angle is 35 degrees, okay? And they tell us that it's 20 meters long and that we're taking it from here to here, but they only want the change in gravitational potential energy. So I could calculate that by doing this. Okay, what's the initial gravitational potential energy? 0, it's at the bottom. If I want to calculate this, all I need is this side, agreed? Okay, so it's the opposite side. So sine of 35 times 20. All right, that side's 11.47 meters. Okay, well now I can go 250 times 9.81 times 11.47 with all the decimals, obviously. All right, so we're going to get 2.8 times 2.81 because we have 3 significant digits times 10 to the 5. Okay, all right with that. Okay, what's the other way? Much, much longer. Could you do it with forces? But oh my gosh, that's a lot more work. You got to calculate a lot more stuff to solve this as an inclined plane problem. Okay, I would not recommend doing it that way. Okay, just because there's so more chances to get to mess up somewhere. Okay, so I mean you could calculate like F parallel. Okay, and then there'd be F parallel. So you'd have to do mg, force of gravity, get F parallel, then F parallel times 20 meters, and then you'd get the same number. But it's more work. I did a trig calculation and then I multiplied it, was finished. Okay, it's shorter. And as we get into more complex problems, there will be ways to solve them using Newton's second law, but they'll get more and more involved as opposed to just doing change in energy. Okay, change in energy is always going to be the faster way. Okay. Now, before I run out of voice here, let's talk kinetic energy. Okay, so kinetic energy is energy you have if you're moving. It is only dependent on 2 things. What 2 things can affect your kinetic energy?
Mass and velocity.
Mass and, yeah, and speed. We can say velocity, but it's technically speed because it's a scalar quantity. All right, now, what's different about this relationship though? Like, yes, kinetic energy is affected by mass and velocity or speed, but which one has more effect?
Velocity.
Yeah, because?
Squared.
Yeah. Right, the other one is just linear, right? It's just m. But because v is squared, it has an exponential effect on the amount of kinetic energy you have. This is why we have special speed limits for different places in town. It's why in school and playground zones, you need to go 30. Because the amount of stopping distance required for you changes exponentially with the amount, with how fast you're going. Okay? It comes down to a very simple work energy theorem relationship. Okay? If I want to stop a car, if I want to slam on the brakes and stop, my brakes have to do enough work to change my kinetic energy from whatever it is to 0. So I'm not moving anymore. Okay? Now, what that would mean is that the work is going to be basically just my final kinetic energy, because my initial kinetic energy, because my final is going to be hopefully 0. I want to stop. Okay, now, here's the work energy theorem part of this. Your brakes can only exert so much force, and it's dependent on road conditions. The distance is how far you're going to travel before you stop, right? The other side is the mass of your vehicle and the speed you're going, squared. Okay, so if I wanted to calculate my stopping distance, it's a pretty simple calculation. It's my kinetic energy divided by the force my brakes can provide to stop me. Here's the problem. Because v is squared, it has an exponential relationship with how far it will take me to stop. If I double my speed, I don't have twice as much kinetic energy. I have 4 times as much. It's an exponential relationship. Okay? If I double my speed, 2 squared is 4. If I triple my speed, how much more kinetic energy will I have? 9, 3 squared. Okay? So if I'm going through a playground zone at 30, I'll stop in a certain distance. But if I'm going 60, for whatever reason, it'll take me 4 times as long, distance-wise, to stop. If for whatever crazy reason I was going 90, okay, it would take me 9 times as far to stop. It's exponentially related. And I can show that to you here pretty quickly. Okay, let's just say that, for argument's sake, my car can exert 10,000 newtons worth of braking force. Okay, so that'll be F. F will be 10,000 newtons. Okay, V we'll start out with 30 kilometers per hour. Okay, so that's 8.3 meters per second. Okay, so, and let's just say the mass of my car is 2,000 kilograms. All right, so if I plug all that in, if I say going the speed limit, I would go 1/2 times 2,000 times 8.3 squared divided by 10,000. Okay, it's going to take me 6.94 meters to stop at 30 kilometers an hour. Okay. Now, if, for whatever reason, I was going twice that speed, okay, I'd be going 16.6 meters per second through that playground zone. All the numbers are the same except for this one. So 0.5 times 2,000, okay, times 16.6 squared divided by 10,000. Okay, 27.7 meters. I'm pretty sure yeah, look at that. It's 4 times more distance. I'm only going twice as fast, but it's going to take me 4 times longer to stop. Now, nobody obviously goes through a playground zone in their right mind at 60 kilometers an hour. Okay? But we're probably all guilty of going, 10's not that big a deal, right? If I only go 10 over, it's really not a big deal. It's not that fast. But what we forget is it's exponential. If I go even 10 kilometers an hour over the speed limit, I'm increasing the distance that will take me to stop exponentially. So if I go, instead, I go 40, okay, that's my speed now. Plug in the same calculation. So at 30 kilometers an hour, it takes me just under 7 meters to stop. At 40, which is only 25% more, it's almost twice the distance to stop. And that's only 10 kilometers an hour. Okay? But it makes a big difference. Okay? It's why you need to go the speed limit in school and playground and construction zones. Okay, there are people there and they're not always paying a lot of attention. Okay, they're either children or they're busy working. Okay, and that's why there are those special speed limits in those zones. There are people who are vulnerable in those places, and speed has an exponential relationship with stopping distance. Okay, police officers understand this. It's why they're so angry when they pull you over in a school zone or a playground zone for speeding. They get just how dangerous that can be. Okay, everybody with me there? Now, added to that could be a distraction. Okay, because I remember once seeing this just outside of Westmount School. A person roared through that school zone at about probably 65 kilometers an hour, and they were on their phone. And there was a police officer there, luckily, that day. I have never seen a police officer tear someone a new one like that day. Okay, like he took her license, okay, towed her car. Okay, that is just beyond irresponsible. Okay, that is not only a speeding ticket, it is also a driving without due care and attention and reckless driving all in one. Okay, that's a 3-for-1 kind of ticket. Yeah? Don't do that. Okay, and I say that because I'm on parking lot supervision a lot. And I see a lot of this as people are leaving the parking lot. I also see a lot of high speed leaving the parking lot. This speed bump is not a jump. Okay? If you scrape, and a lot of you do, going over that bump, you're going too fast. Okay? That bump is designed to slow you down. If you scrape, that is your signal you were going too fast. I feel bad having to explain that, but some people don't get it. Okay? Because I see the same people scraping every time I'm on supervision. It just boggles my mind. Okay? Go slow. Okay? It's helpful. Okay? As a parent, okay, of people that could be in a playground zone or a school zone, okay, please go slow. Right? That 10 kilometers an hour doesn't save you that much time. I mean, if you do the math, a typical school zone or playground zone might at the most be 400 meters, probably not, probably only 300 meters in length. So if you're going the speed limit, so 8.3 over 300 meters, okay, it's going to take you 36 seconds at the speed limit. Okay, you're going to save 9 seconds. You're still going to end up at the same damn red light the other guy did. Okay, like whether you went the speed limit or not, you're still going to end up at a red light when you get there. Okay, I don't know how many times I see that. Somebody actually passed me in a residential neighborhood one time, and then I ended up behind them at the light. We'll keep to ourselves the gestures that were made when I was behind that person at that point. Okay, it was reckless for them to do that, and it didn't get them anywhere. They ended up at the same light as me. Yes, sure, they got there, 10 seconds before I did, but guess what? Hurry up and wait. Okay, that's usually what happens. You don't really get ahead. Okay, so drive carefully. Your car is a weapon. Treat it as such. Okay, I don't mean kill people with it. I mean, be careful, treat it with respect, be careful with it, okay? All right. So, on a highway, we've got two different vehicles. We have a car that is 1,200 kilograms moving at 20 meters per second, and we have a loaded van that is 4 times heavier, okay? Moving, and it has the same kinetic energy, okay? We want to figure out how fast this van is going. Right now, it has 4 times more mass, but it has the same kinetic energy. Okay, so can we calculate the kinetic energy of the car? We have its mass and its speed. Okay. Okay, so that car and the van have 240,000 joules worth of energy. Now, I want to figure out how fast the van is going. Okay, so I want to solve for the speed of the van. So I'm going to divide both sides by 1/2 the mass of the van. Okay, sorry, I got to make that small so we don't get confused. Okay, and then I got to square root that. That's too many zeros. Okay, now it's going half as fast. Could I have kind of done that in my head? The car is 1/4 as heavy. So if I'm talking about the van, which is 4 times heavier, but it has the same kinetic energy, it has to be going half as fast. Okay? It has 4 times as much mass, so it has to have half as much speed. Okay? I mean, obviously, it doesn't take very long to calculate that, okay? But there's a shortcut for that if we understand that relationship. Okay? Okay, try number 3. Give you a few minutes on that one. Change in kinetic energy this time. Change in anything, still final minus initial, so don't overthink it. Increase in kinetic energy here, it's just going to be final minus initial. Right? So change in kinetic energy will be 1/2 times 65 times 4.2 squared minus 1/2 times 65 times 1.75 squared. Okay, and we should get for that then 474 joules as the difference there. Okay, questions on that one? All right, so I'd like you to do, I'll blow this up so it's a little bit bigger, but let's do question 2 first, and then we'll talk about it, and then we'll do question 3.